Let us discuss the few problems from electrophilic aromatic substitution. So let us copy this one. Now what I am asking is, this molecule is called furan. So this molecule I have a furan. Now if I do bromine and this is ether as a solvent, dioxane. So this is a solvent. If I treat this compound with bromine, Br2, electrophilic aromatic substitution happens in this case, and bromine attacks on position number 2. So this is a case of electrophilic aromatic substitution. Br plus forms, and then you see this compound is basically aromatic, 2, 4, 6. sp2, 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 sp2 and sp2. So this compound is aromatic. Now if the Br2 adds, it adds on position number 2. So you have to prove why this adds on position number 2, why not on position number 3. So you see there are two kind of position, this position and this position. Basically this position and this position are identical, equivalent. This position and this position are equivalent. So why it adds to position number 2, why not at position number 3? Now you know the answer. What you will do? You have to attack an electrophile and position number 2 and make the resonating structure. Then again you attack on electrophile on position number 3, make the resonating structures. If you find resonating structures at 2 are more stable than resonating structures at 3, this suggests reactivity of carbon 2 is more than reactivity of carbon 3. This is one way. Another way you can also prove, you can basically see, okay, let us do this one and then we'll discuss for the next way. So what you have to do is you attack a electrophile on position number 2 and see the resonating structure. Attack the electrophile on position number 3 and see the resonating structure. Okay, have you done? Now let us see the solution. What we can do is, let us say if I attack at C2, I will have attack at C2. So this is happening. So this pi bond is breaking and this attacking on bromine, this goes. So I will attack bromine on position number 2, attach, and then here we will have a positive charge. So this goes here, so we will have a positive charge here. So let us write this one. So if you attack at position number 2, you will have something like this. Now you see, you can write resonating structure of this molecule. So this molecule will have many resonating structure. I can write resonating structure for this molecule. So these are the possible resonating structure for this molecule. You see, if I flow, so this is the structure I am writing here. So this is 1. So let us write here 1. So if I write 1 here, so this is my 1. I can always write Now you see, so this is a structure number 1. Now if you flow this electron pi bond here, you will have a positive charge here. Now this is a structure number 2. Now if you flow even more this electron this side, you will have a resonating structure 3. So you are getting 3 resonating structures in this case. Everybody agree? If everybody agree, then I can go further. Now let us attack on carbon number 3. So if I attack on carbon number 3, so there are 3 resonating form in this case you have. If I attack on carbon number 3, so there are 3 resonating structures. If I attack on carbon number 3, I will have something like this. So C3, attack at C3. So this means this electron goes here, this goes here. I have to add bromine here. So if I add bromine here, I will have something like this. Now I can write resonating structure for this molecule. Are you getting or not? So this goes here, this goes here. So you will have Br attached here and you will have 1 Br minus inorganic product. I am not interested. Now I can write resonating structure for this molecule. So if I start writing resonating structure, so let us call this as a 1. If I call this as a 1, so now let us write the resonating structure for 1. So if I write 1 here, so this is 1. Now I can flow this electron this side. So why I have only one option? I can flow from this side. I cannot flow from this side. You see, there is no conjugation with this pi bond. So I have only one option. I can flow from this side. So now this is resonating structure 2. Now you see, in this case you are getting only 2 resonating structures, and that's why attack happens at carbon number 3, carbon number 2, not on 3, because if you attack on 3 you have only 2 resonating structure. Are you getting or not? Okay, let us write this one and then we'll go for the next problem. Now the next problem is something related to iodination of benzene, benzene. Okay, so let us go for this problem. So let us copy this one. So we have something related to iodination of benzene. So this is iodination of benzene. If you remember, chlorination, bromination can be done using Cl2Fe. That is halogenation using Fe plus Cl2, Fe plus Br2. But fluorination and iodination cannot be done. 2 reasons. Fluorination is too reactive and iodination is too unreactive. So I can say I cannot add fluorine because of too reactive. So I can say F2 too reactive. You're getting? So F2 is too reactive and I2 is very less reactive, the opposite. I2 is very less. So this is very less reactive. You can write. So this is I2 is very less reactive. And that's why iodination cannot be done simply taking I2 plus Fe. So what we do is, we take a oxidizing agent HNO3 that forms I plus. So what we do is, HNO3 is taken as oxidizing agent, and now in this case you have iodination. You're getting? So to do iodination, what we do is, unreactivity of iodine is increased by adding HNO3. So if I add HNO3, R2 plus HNO3, and in this case iodination can do. So HNO3 is acting as a oxidizing agent. So this is a basically oxidizing agent. So what this is doing is, this is oxidizing I2. So let us write on the mechanism for this reaction. So I will give you some hint. You have to remember some inorganic chemistry reaction I2 plus HNO3. And then you can write this product. So I2 plus HNO3, I2 oxidation state 0. I can increase. I will have only one option, I2 plus, I plus. So let me write. Anybody can try. And one product is NO2, another product will be I plus. So you can write the reaction I2 plus HNO3. That is an inorganic chemistry reaction. So if you can write that one, and then you can simply electrophilic aromatic substitution. So let us see the answer. So what you have, here you have I2. This I2 reacts with HNO3, it forms I plus. Are you getting? Now this I plus is called iodonium ion, like it's a halonium ion, bromonium ion, chloronium ion. So I plus is called iodonium ion. Are you getting? Now you are getting another product as NO2. So you have to remember in this reaction I2 plus HNO3, I get I plus NO2. Now this iodonium ion can further react in the, now things are easy. Iodonium ion can react with the benzene ring, that is electrophilic aromatic substitution. Loss of H plus final gives the product. Are you getting? So you see here, so this step you are already familiar with this step. Did you agree or not? So you are familiar with this step. Okay, let us go for the next problem. So I think how many you have written? All of you have must written. So let us go for the next problem. Now this molecule has a name, that is PHCH2 double bond CH2. This molecule is called a styrene. So let me write here. So this molecule is called a styrene. So this is a styrene. So this molecule has a name, and this common name, of course. This is called a styrene. These molecules have common name, more popular. So this molecule is called a styrene. Now question says a styrene reacts faster than benzene in electrophilic substitution with E plus. If you react this compound with E plus, a styrene reacts faster than benzene. Why this is so? A styrene reacts faster than benzene. Why this is so? A styrene reacts faster than benzene. Why this is so? Can anybody tell me? I will give you a hint. In this case, this double bond can act as a R plus R group. It can basically increase the electron density in the benzene ring. Are you getting? You can, what you do, you attack on electrophile either on ortho position or para position, and then you write down the resonating structure, you will get the answer. You're getting? So you attack on ortho position or para position, you write down the resonating structure, you will find the answer. So let me see. Some of you have done this one. Let us do ortho attack. So if I attack on ortho position H plus, I can have any electrophile, or E plus. Let us take E plus if you have any confusion. So let us take E plus. If I take E plus, I can add electrophile here. Are you getting? So if I take E plus, so this is reacted with E plus, I will add E plus here. Now this plus is gone, so EE. Now I can write resonating structure for this molecule. You see, there is E basically. So in this case, this is E. This is also E. Sorry, this is at ortho position. Okay, good. So this is also E. So if I attach electrophile, now I have plus, I can have one extra resonating structure due to this double bond, that is the conjugated. So this goes here, so I will have plus here. Now rest of the other resonating structure I can always write. This goes this side, this goes this side, plus this goes this side. So if I flow this arrow, so I can come from here to here. If I flow this arrow this side, I will have a positive charge here, so I can get here. If I flow again this arrow here, so let us say I will get one more resonating structure. So this is this. If I flow this arrow this side, I will get positive charge here. This side positive charge here. So this is the third resonating structure. So you see, we can write resonating structure, more resonating, at least one more resonating structure. This resonating structure, that is extra. So I am getting this extra resonating structure if I attack at ortho position and I have a styrene. Similarly, I will get same kind of resonating structure if I do attack on para position. Are you getting? So this suggests me that a styrene molecule is more reactive than benzene. In the case of benzene, I will not get this extra resonating structure. So this extra resonating structure makes carbon ion, makes erinium ion more stable. Are you getting or not? So that's why attack happens at ortho and para position, and rate of this reaction increases with respect to the benzene ring because of this extra plus extra stabilization. Are you getting or not? So let us copy this one if you have not done it. So let us copy. I think these things are easy basically. Have you written this one or not? If you have written, we can go for the next problem. Okay, let us go for the next problem.